And there are different ways of doing it. Textbooks typically like to keep n to be an integer and have a different formula. I prefer to keep the same formula and then just have a different values for n. So what I prefer to do is to say this is n lambda, but now n means something different. To get this list, I want these to be what are called half integers, which are even numbers. Sorry, I missed what said that. Odd numbers over 2. So 1 half, 3 halves, 5 halves, so on. They're halfway between integers, which is adjacent integers, which is what they mean by half integers. It doesn't mean an integer divided by 2. It specifically has to be an odd number divided by 2. Okay, so this is where you have to be in order to have constructive or destructive interference. And it's true for light or for water waves. Either one is true. So they usually write the formula just as delta x equals n lambda, and then I'll say that we'll give this to you, and then I'll just leave you to know that if n equals 1, for example, it's constructive. If n equals a half, then it's destructive. If n equals 3 halves, then it's destructive. If n equals 5, it's constructive. So you just have to kind of identify is which of the list type of numbers does it belong to. Is it an integer or is it a half integer? If it was equal to, say, 1.75, then it would be partial, which is not either of those cases. Now, this is pretty good. I now figure it out everywhere I can be, where it'll be, to figure out at any given point how to figure out if it's bright or it's dark or whatever. The way that I would do that is I would measure the distance to each of the two slits, which are the whatever two sources of waves, and then I would just measure how much farther one is than the other, and I would solve for n, so I divide by the wavelength, and I would get a number like 3 or 1.5, and then I'd see, is that number an integer, or is that number a half integer, or whatever, and then I'd be able to know if it was constructive or destructive or what. But the problem with that is that it's pretty easy to get the wavelength. Usually for light, you can get that because a laser will tell you what the wavelength is. You know what wavelength it is pretty easily. But it's really hard to actually measure how much closer one of these sources are than the other. Because if you don't remember, these slits are like really, really close to each other and very, very teeny. So the difference in distance is extremely small. You can't take a ruler or a yardstick and measure it. You're just going to get the exact same number as the distance to two of them. And if you subtract them, the difference in those two distances is so much smaller than the uncertainty in your measurement that you can't effectively measure the distances individually, subtract them, and get the right difference. You just can't be that precise. So what we're going to have to do is we're going to have to find a more clever way of finding delta x. And that's going to involve math. This math. Okay? So I'm going to try to show you what this math means. What I'm showing here is a zoom in on the two slits. Okay? So these two slits here are the slit here. So I'll call this slit 1. And this down here is slit 2. I'm going to call the distance between them d, lowercase d. Everybody does. Now, what I'm going to note is that if the two sources, the location where I want to know what type of interference is pretty far from the slits compared to how close the slits are together. Like normally they're, maybe much less than like 1/10 of a millimeter apart. And so if you're like a meter away, you're talking about 10,000 times. You're 10,000 times further away than the distance between the two slits. And so this scale picture right here is not at all to scale. In reality, if I wanted to do this to scale, this dot would be so far off the right screen you wouldn't be able to really see it at all. And in that case, these two lines are almost exactly parallel. Of course, they're not going to be exactly parallel. They'll meet up at some spot, but they look very close to parallel. And those two lines are these lines here. This one right here, and this one down here. And they're basically parallel. This is what this is trying to show you, is that this right here is basically a right angle. Okay? These are the wavefronts coming out from those two. And the idea is that this distance to the point where we want to know the interference is the same as that distance. Okay? So if they, at this point, are doing the same thing, they'll go off, and then crest will eventually go and hit that point, continuing to do the same thing. So this amount of distance, if I want to do the difference between x1 and x2, which is that to the point and then that to the point, these parts would cancel out. And all you will be left over with is this part, delta x, which is that side of the triangle. And we'll use this angle, which is approximately the same thing as that angle. If this is 90 degrees, it's exactly the same thing, which is measuring in this picture. And I'm going to draw that angle here. So there's to the center dot, there's an angle. So if I want to know the interference here, and then there's a central location that just splits the slits in half, then this angle right here is theta. It's how many degrees off from the center are you? And that's the same thing as this theta, and it's the same thing as that theta. And if I look at this triangle, which is a right triangle, I can say that D is the hypotenuse, delta x is the opposite, and so therefore sine of theta, opposite that angle, is delta x opposite over the hypotenuse, D. Well, in other words, that delta x is D sine theta. This is just a math trick, a trigonometry trick. It has nothing at all to do with the physics of light, waves, and so forth, but we will use this fact in our discussion of light waves, because this is going to be a much more effective means of measuring delta x. That if we know the distance between the two slits, say the manufacturer told us, for example, then what we can do is measure the angle much more easily. And if we have the angle, that gives us delta x. Okay? So usually written delta x equals d sine theta. Math fact. Okay? Or I should really say approximately is equal to d sine theta if it's far away. That's the math fact. Now, we're going to put these two parts together, and we're going to say d sine theta equals n lambda. Okay? Both the left and the right are the delta x, or the amount extra that you are closer to one slit than the other. So the idea is that the locations where you're at constructive or destructive interference occur at certain angles. And for example, if you're in this central bright spot, you're equally distant from each slit. So your delta x is 0. And if delta x equals n lambda, then n is 0. And if you plug in n equals 0 here, theta has to be equal 0. The next bright spot off to the side is where you're one wavelength closer to the top slit than the bottom slit. So delta x equals 1 wavelength. And if you knew d, you can find theta here. That will give you the angle at which this is offset to the side. Same thing with 2, 3, 4, and so on. Now note, I don't want to give the impression that n can go as high as you want. There is a limit on how many spots there are where you have constructive interference, off to the right here. And the reason is that d sine theta can never physically be larger than d, the distance between the two slits. What this means, physically, is that you can never be closer to the top slit than the bottom slit than the distance between them. So, to make this clear in another way, say I have two speakers on a table, and they are 1 meter apart. I can never be 2 meters closer to one of the speakers than the other if they're a meter apart. You can try it. Set up two things on a table that are a foot apart. Just try to stand somewhere where you're 2 feet closer to one of them than the other. You can't do it. Physically, you cannot do it. And so what that means is that you can have n values, so you can plug in and tell the right-hand side can get up to d. So you can, if, for example, d is 5, and the wavelength is 1, in whatever units you want it to be, nanometers, whatever. Then you can plug in n equals 0. That's fine. You can plug in n equals 1. That's fine. 2, fine. 3, fine. 4, fine. You can do 5. You cannot do 6. Okay? So I could plug in n equals 0, 1, 2, 3, 4, 5. I could also plug in -1, -2, -3, -4, and -5. There would always be some angle that worked for. So overall, that would give me 11 different values of n that were integers I could plug into that formula. That would mean there would be 11 bright spots if this was two slits that were separated by 5, say, nanometers or microns, whatever you want, and the wavelength was 1, say, of whatever units you want. That would be how many bright spots that would appear. It wouldn't be an infinite number. It does. I don't want to give you a sense that the number of dots just keeps on going on and on and on and on forever. And if you want to find out where the dark spots are, because that's destructive interference, those are the spots where it's half a wavelength closer to one top than the bottom, or 3/2 of a wavelength, and so on. That's where you just have to plug in to 1/2, 3/2, and so on, in for n. Okay. Now this equation here can be used in several different ways, and we'll be using it a lot. So, like all equations, you had to have all of the variables but one, and then you solve for the other one, and you get it. So this can be used to measure the wavelength of light. Find lambda. That's not uncommon. That's one of the main ways that you actually find the wavelength of light, is to use something like this. You can use it to measure the distance between two slits, or two similarly small things that act like slits. That's very, very common. This is actually how they measure very, very small distances very often. You could use it to find an angle that the light will come out at. If you say, I know what I'm going to shine some light on some slits, what do I see? Instead of taking what you see as a measurement, you want to predict out what you should see. You could say, I know at some angle what the a certain distance apart this for slits, I know the wavelength of light I'm shining on it, and I want to say what do I have at a certain angle. I would want to find n and figure out if that's a half integer, an integer, or so on, to find what type of interference. Now, one thing is that the reason I've labeled this down what the n's are is you should be able by eye to know what n is for a given location. So if I know I'm in the central spot, n equals 0. If you're on the next spot over, n equals +1 or -1. And the top one is the one above it is either +2 or -2. So when you do this, you should often be able to know n by eye, and then you solve for one of the other ones. And note, for each different n, there is a different theta. And often it's written, and I kind of prefer this way to write it, is theta sub n. So there's an angle for every n value. So like there's an angle for this first bright spot, there's an angle for that second bright spot, an angle for that bright spot, and so on. And so there's a different angle for each value of n.